Here I will introduce our work in multiview representation learning for the COVID-19 diagnosis. This work is finished with United Imaging and several hospitals. Okay, we know that the current clinical experience shows that the nucleic acid testing have a very low sensitivity, especially in the early stage of infections. Fortunately, we can got a lot of chest CT images, and these images often contain effective information for diagnosis of the pneumonia. Okay, so it is necessary to complement nucleic acid testing with automatic technique based on the chest CT image. Here is some examples of the chest images with infection of COVID-19 and with the CP infections. According to these examples, we can find that firstly, for some examples or for some patients, they are very similar for the corresponding CT images between different types of pneumonia. Okay. So a question is, if we just use single view features or simple features, maybe it's insufficient for diagnosis. So we in this work, we want to type of features may contain complementary information, so it will be beneficial for the subsequent tasks.
Sorry, Changqing, can you turn your video off a little bit?
Okay.
Traffic problem, internet traffic. Oh yeah. Okay, good. Thanks.
Okay. Specifically, we can extract the radiomic features and some handcrafted features. Of course, we can divide them into several groups according to their different meanings. For example, radiomic features can be divided into grid features and text features. The grid features are composed of the first-order statistics which describe the distribution of voxel intensity within image regions, such as maximum, minimum, median, and so on. And the text features are derived from some grade level statistics metrics. Okay, we should note that all these features are extracted after segmentation, so they can provide valuable local information. This information has incorporated expert prior. Okay. For this data, this is a subject. Okay, I can show the point. This is a subject distribution in terms of genders. We can find the number of male and female are comparable. Okay, but this is a subject distribution in terms of age. We can find the average age of the CAP subjects is much older than the COVID-19. Okay, it is easy to be understood. So the first nature idea is coming. What about the quality of these different types of features? We evaluate this from two different perspectives. Firstly, we visualize each type of features by directly mapping them into a low-dimensional space by using some dimensionality reduction method. Okay, for example, the famous TSNE algorithm. So we can find that all these features cannot well reflect the underlying classification or class labels. However, it is difficult to say that these features are not promising for classification because the visualization simply treats each feature with equal weight. However, in classification, we can learn different weights for different features. So we also conduct experiments by by using different features on different classifiers. These classifiers are some very baseline models. Okay, from this figure we can find that the performance is not so bad as in visualization because it uses weighting strategy for different features. Okay, we can find another fact that the concatenated features, that is using all the features, combine all the features, achieves much more promising results. So we want to ask another question: is there any strategy or any model we can use or we can design to further promote the diagnosis accuracy? To answer this question, we propose our model. We call it structured latent multiview representation learning. The main advantage of the model is the completeness and structured representation. Okay, the first one, the completeness means we can encode the information from different views. In our work, there are 7 types of features into a latent or a compact low-dimensional latent representation. How to achieve this? Okay, let's see our first step. In our first step, we call it learn, complete, and structured latent representation. Okay, for the completeness, we use a backward or degradation network groups. For each type of feature, we use 1 networks. The latent representation is randomly initialized. Then, if the latent representation can degrade through each network to a type of feature, then the information from this type of feature will be encoded into our latent representation. Okay, so we call it complete latent representation. Okay, for another property, we call it structured representation. Because in training we have data, we have class labels, so we want to use the label to guide the learning to make our latent representation have promising structures. Then it can be benefit for the subsequent tasks. Okay, to handle this issue, we design a non-parametric loss. This loss is very simple. It is a clustering-like loss. The detail can be found in our paper. Okay. So in the first step, we can learn the latent representation from multiple types of features. Okay. The second step, we call it learning projection from the original features to the latent representation. So how do we really need the second step? Yes, because in the first step, we need labels and original feature, but in the testing stage, there is no label. There is just multiple types of features. So we learn the direct mapping from the multi-view or multiple types of features to the latent representation. Okay. After the second step, we can learn a very simple classifier. For example, a 3-layer fully connected network to classify the latent representation based samples. Okay. So in the testing stage, given a subject with multiple types of features, we use the projection regressor to get the latent representation and then input the latent representation to the latent representation based classifier can go to the final results. Okay, we know that the completeness and the structure are very, very important for the model generalization. There are some works have shown that the reconstruction, for example, the autoencoder can help our model have more much better generalization abilities. And this structure, in fact, it introduces simple induced bias. So it will further enhance the generalization ability of our model. Now we will evaluate the effectiveness of the latent representation learned from our model. Okay, according to the training data, we can find that the learned latent representation is well structured, which is consistent with our ground truth classes. Okay, this is in training stage because the label, class label, or ground truth is available. Okay. What about the performance in the testing stage? We can find that the left is the original testing data, and the right, or the subfig D, is the learning latent representation for testing data. We can find that after the projection, our latent representation is very consistent with the ground truth. Okay, so we conduct experiments on different baseline classification models with the original features. We just concatenated all these features, all original features together, okay, and then use our learned latent representations. We compare them, okay. We can find that all the shallow models perform not promising. They are all below 19%, 90%. The neural network performed generally better. All methods which also use the latent representation on the neural networks further improve the results very significantly. To more comprehensively evaluate the representation, we ran different classification models. All these models are some baseline models with our learned representation and the original features. According to these features, we can find that, according to these figures, we can find this model with all learned representation as shown as the yellow bars outperforms that using the original features. Okay, in all the metrics and in all by using all the baseline models, it validates the latent representation can be widely used on different classifiers. Okay. To evaluate the stability of our model, we run our model on different ratios of training data. Of course, the testing stage testing data set is fixed. When using a very small training data set, the performance is also promising, and with more training data, the performance is further increased in a big picture. Okay. So this is the conclusion. Firstly, we can find that multiple types of features is really effective and necessary. Okay. Secondly, neural network is very effective to explore the general or nonlinear correlation between the latent representation and the class ground truth. Okay, the third one is the structured representation and the preserving the intrinsic information, or we call it completeness, is very important. They are all very important. They can jointly enhance the generalization ability of our model. The last one is that all latent representation can be widely used on different classification models. Then the promising accuracy can be expected. So if you design another advanced classifier models, you can try our latent representation, and maybe it will further improve the results. Okay, so compared to the end-to-end stage, our model is not an end-to-end model. Okay, so but our model is quite effective and stable, where the possible reason include the complementary features, and these features incorporate expert prayer. Another reason is our advanced latent representation proposed produced from our model. Okay, thanks.